Oh, thanks. Hi everybody. I will say a bit about what the AI department was doing last year. So we are 4 groups. We are the group of machine learning led by Robert Babuška, foundational AI led by Tomáš Mikolov, then formal methods led by Mikuláš Janota, and automated reasoning led by Tinsuda. Last year we were in a bit of a funding trouble, which looks like kind of getting better now. So we have actually grown from 18 people to 24. We have like 6 more people now. We supervise or co-supervise roughly 11 students, one defended in 2024. You will see 4 presentations of 4 papers in total. We did I don't know, 5 in journals, 22 in conferences, 16 workshops, and 3 book chapters. And there is a bunch of projects that have been already running, like RoboProx, headed by Zdeněk, but in our group by Robert Babuška and Mikuláš Janota, started officially in 2023 already. We still have the ERCCZ project of Mikuláš Janota. We have a Marie Curie fellowship by Jonathan Huerta Munive, the Corsens project, and the Formal Ethics project funded by Cisco. We have started in 2024 the ERCCZ project by Tomáš Mikolov. That's very good, even though the ministry is still making some problems to us. Martin Suda got his own new gadget project in machine learning for theorem proving. We are part of the SEDMO funding, and I got a small Amazon research award last year. And in 2025 we will start my XPro project, and a project funded by a company called Novamente in cognitive inference control, and also the Elliot project, where it's headed by Robert Babuška for our department. Some awards that we got to, you may have noticed that Tomáš Mikolov got the AI award this year. The vampire team represented in our group by Martin Suda and Petra Hozová has won a really big victory in 2024 in the World Championship of Automated Theorem Proving. So they really did an amazing improvement over the last year version, and they basically won almost all of the categories. We got one Best Paper Award. Petra Hozová was a finalist in a PhD award at the TU Vienna. And as I said, I got the Amazon Research Award. We have organized a bunch of conferences, and I will not go into it, and done a bunch of invited talks. Tomáš Mikolov is doing a great job in media appearances. We are doing AI lobbying in Europe and Czech Republic. And also Tomáš Mikolov has a new startup where he's trying to make LLMs for practical use. So that's my introduction. And you will now see 4 papers by the 4 groups at our department. The first talk is going to be given by Jirka Kubalík about the SymFormer.
Good afternoon. My name is Jirka Kubalík, and thank you for the introduction. And I'm going to talk about our paper SymFormer, end-to-end symbolic regression using transformer-based architecture, which is the result of the work of our group led by Robert Babuška. First, what symbolic regression is. Symbolic regression is a method that automatically generates models as analytic free-form formulas. The free form is important. That means that the problem is not just in quotes, it's not just tuning some parameters of formula of some predefined structure. The problem is twofold. First, find the structure of the formula and find the coefficients of the formula. So in the history, there have been many approaches. Historically, the most prevalent method for symbolic regression is genetic programming, which is gradient-free evolutionary optimization approach, which involves a population of candidate expressions. Am I going back or forth? Yeah. Expressions and sampling new expressions by simply exchanging parts of the expression trees between two or more expression trees, or by modifying one expression tree. This method is good at global exploration, but fine-tuning of the coefficients using just the blind genetic operators is challenging. Then there are neural networks, classical feed-forward neural networks, which typically work in a way that they start with some redundant topology and try to optimize the weights of the topology in a way that there are only few active nodes and few active weights in the end, which then represents a simple analytic formula. Thanks to this gradient-based approach, it's good at fine-tuning the coefficients, but on the contrary, but it is not so good at global exploration. It is prone to get stuck in some local structure. So an important message is that both approaches start learning the formula for the new data set. They start learning the formula from scratch. So the inference time is computationally high and computationally demanding. Now we turn to transformer-based approach, which is the topic of our paper. We proposed a transformer that is trained on large collection of formulas to generate mathematical expressions directly from a new set of input-output samples. So the main features of the method are that the training data are not anymore a set of input variable vectors. Instead, the data are tuples composed of dataset samples and the corresponding formula. So we need to somehow pre-process the data before they enter the transformer. We used a set transformer that generates embeddings of the input data samples in such a way that the embedding is invariant to permutation of samples in the data set. Then the important part is that it works in such a way that it jointly predicts the structure of the formula and its coefficients, which differentiates, which distinguishes this method from other methods based on the transformer. We also used an extended encoding method for constants, and we use optional optimization, which is optional optimization which is optional part of the algorithm that optimizes the parameters of the formula. So the advantage of this approach is that once the transformer is trained, then given a new set of data samples, it generates the formula in a matter of seconds, for example. So the inference time is very short compared to the genetic programming and neural network approaches. I have not many. So I will skip those details and go directly to some results, which I believe are interesting. In this work we focused on univariate and bivariate problems. Sorry, I always do it wrong. So there are on the right there are two examples of formulas generated by the transformer given new data set where the ground truth is the blue line and the predicted or generated formula is the I don't know, orange one. So we can see that it is able to pretty nicely generate the correct structure of the formula, and also it fits the coefficients almost and exactly. And the same holds for this example 2D function. There are more results, like our approach is more time efficient than the compared approaches. Our approach also, or the transformer, is able to extrapolate to the data which are sampled outside the training distribution and so on. So many interesting features. So concluding my talk, the advantages of this approach are, as I said, the inference time is very short. The extrapolation capabilities are very good. Disadvantages also. As always, this approach has also disadvantages, and the most significant disadvantage right now is that the number of dimensions and the sampling range are given by the training data set. So what it is trained for, then the best performance is observed on the same problems. So that's it. Yeah. Thank you very much for your attention.
Okay, so my name is Hula, and I will talk about graph-neural networks and language models in the context of reasoning. And the work is based on this paper which is mentioned here. And the motivation for this work is that we would like to come up with a mental model for how to think about language models and other types of graph-neural networks. Because I think most of us are excited or surprised by the current models like ChatGPT. And some people even claim that in a few years we will have models which will be able to do research and which will be able to do like design algorithms. But we don't know whether this is possible because we don't understand what these models are doing, and we also don't understand what is required to do things such as research or design of algorithms. And one interesting ability of these models is the ability to do reasoning. And it's also a very dividing topic because some people say very confidently that these models are just memorizing training data or they are detecting some patterns. And some people are very confident that they are already doing reasoning. So we focus on this, but because it's not very well defined, we study it in the context of Boolean satisfiability. And in Boolean satisfiability, you have logical formulas, which is a conjunction of clauses, where each clause could be a disjunction of literals. And literals could be either original variables or negated variables. And we have such solvers which can solve formulas with millions of variables, so we are not trying to compete with such solvers. For us, it's just a domain on which we can study, you know, the ability of neural networks. So we study only formulas with up to 100 variables and several hundred constraints, which is already very difficult for humans. Like, for example, humans could not solve such formulas in their head. And before us, there was already a paper which showed that it's possible to train a graph neural network to predict satisfiability of such formulas. And they did it by encoding the formula as a bipartite graph. So on one side of the graph you have literals, on the other side of the graph you have clauses or the constraints, and then they do message passing, where every round of the message passing they would update the embeddings of these nodes. And they initialize it by random vectors, and after each round of the message passing you would update these vectors. And they do 30 passes of message passing, and then they took the embeddings of the variables, and from this they predict whether the formula is satisfiable or not. And they showed it's possible to train it to high accuracy, but there was no explanation why is it possible, why it should work. So we tried to understand this, and we looked at the low-dimensional projections of these embeddings for variables after individual time steps. So each time step could be understood as an application of one layer. So basically we are visualizing what happens after each layer. And as I said, initially it was initialized randomly, so it's a random point cloud, but if the formula is satisfiable, it will converge to these two nice clusters. And if the formula is not satisfiable, you would have random points. And so this image for us triggered the idea that maybe what these models are doing, they learn to act as a solvers for semi-definite programming relaxation of max-SAT. And max-SAT is an optimization version of SAT, where you try to maximize the number of satisfied clauses. And how you do it, you form max-SAT as an ILP problem, where you have binary constraint which tells you that the variables should be binary, either -1 or +1. And you can design approximation algorithms from that by doing relaxation. So you relax this, instead of optimizing over these binary variables, you optimize over interval from -1 to +1. And this is linear programming relaxation, and once you solve it, you need to round it to the nearest integer, and then you have a solution. And this algorithm will come with a guarantee which tells you that in the worst case, you will not be very far from the optimum. And you can design better approximation algorithms with better guarantees, for example, with semi-definite programming, where instead of optimizing over this interval, you take these variables, you lift them into vector space, so now you have a unit vector for each variable, and you optimize these vectors instead of these scalars. And so, what you would see if the formula is satisfiable, you would see that the variables would create very nice clusters. So that was our mental model for what these graph neural networks are doing, and then using this mental model we designed a few tricks. So first thing is that if you believe that the GNN is a solver, you can train it for maybe on few iterations, but then in test time you can increase the number of iterations maybe to much larger number. So we train on 30 iterations, but then in test time we increase it to 1,000 iterations. And suddenly we can solve more difficult problems. And another thing is that originally when you train on everything, it's very hard to train because a long time the model doesn't learn anything. And so we designed a curriculum where we start with small problems, which doesn't require a lot of iterations. And once we reach some accuracy on the small problems, we increase the problem size and also the number of iterations. And in this way, we are able to train it like 7 times faster than the training on everything. Then we also do the same thing for transformers, which could be understood as a special type of graph neural network where the graph is represented by the attention matrix, which needs to be trained from data. So this is harder to scale because it's harder to learn, but it's still possible. We are able to train transformers for formulas up to 20 variables. And then you can also generalize it to general constraint satisfaction problems, where instead of having this binary Boolean clauses, you can have generic predicates like, for example, X is brother of Y or Y is bigger than Z. And then you can encode word problems in this language, and you can train transformer to solve it, and you can explain why is it possible. So, like on this toy example, we can explain why language models can do reasoning. And that was still a very artificial example. So here is a real example which I took from this paper, where somebody asked ChatGPT to write a proof of Euclid prime number theorem, which is at the same time a poem. And you can view it as two constraints. One is, proof, and the second is a poem. And the model probably never saw these two constraints together in the training data, and it was still able to, synthesize something which satisfies these constraints. And this is much more, of course, difficult because there are a lot of implicit constraints which are not mentioned. For example, that it's grammatically correct and so on. But we hope that our view that we view language models as CSP solvers, that will help us to understand what's going on and also to design better architectures and also drastically reduce the training time, because currently it's probably extremely wasteful how these things are trained. So that's all. Thank you very much.
Greetings. My name is Koutenský, and I will be talking about our work called Unlocking Nature Design to Neuroserver Automata. And I presented this paper last year at the Artificial Life Conference. And a disclaimer, this will be more of a fundamental research, but even for you who care about the practicalities, it can turn into it, and it's also beautiful, so we will see. So in nature, the complexity arises from simplicity, like patterns form in clouds, ripples form in sand, and the bacteria, they self-organize into bacterial colonies. There is, unfortunately, it is not working, but never mind. There was a process of a bacteria growth, and it was described by these partial differential equations. And if one actually examines such a process, like bacterial growth process or some other process, usually the target is to have the partial differential equations, which represents like this deep knowledge about the process. Because once you have it, you can do predictions about the system, and you can do everything. You know everything about the system. And so it's actually similar to what one of my colleagues presented here before, the SymFormer, I think it was. So it was the idea of doing symbolic regression. The aim of our work was actually similar, and we also wanted to extract these kind of laws from a snapshot of the studied process, and we aimed to study this kind of biological process that unfortunately you can't really see, but it doesn't matter. So first we had to select the process that we want to study, that we want to use to fine-tune our method on, and naturally we turned to the master of the pattern in nature. So the dog. No, I'm just kidding. It's the leopard, and there are two reasons for that. The first one is that the patterns on the leopard's skin it's actually beautiful intrinsically. And the second reason, more pragmatic perhaps, is that there is research established around it, and it gave us a basis for our research. So we used the result of this paper, where the researchers handcrafted models for producing this kind of patterns that actually correspond to the code patterns of the leopard in different stages. It's like 2 days, 8 weeks old leopard and the adult leopard pattern. And what we got, it's these 3 images. It's only thing we got, and our goal now is to train a model that will make the transition from the first pattern, the spots pattern, to the rings pattern, and then to the third pattern, to the rosettes pattern. And while doing that, we also want our model to give us the solution, the PDEs for this kind of process. And to do that, we utilized neurocellular automata. So neurocellular automata, it's like ordinary cellular automata, but with the difference that the rules are now learned by a neural network. And this diagram shows the progression from step 1 to step n+1 for a cell X at the position X. So what we does is, or what the NCA does, the neurocellular automata, is that it applies some predefined filters. It does a convolution operation. So for each filter, we get a perception vector. And once we have these vectors, we can just pass it to some feed-forward neural network. And since all of this is continuous, there is nothing to stop us to use gradient descent to train this method to give us the results we want. And all this is done in a stochastic manner, so that the system cannot rely on any global clock. And this is how we trained the NCA model. So, as I said, we only had these 3 images provided by the paper that I showed you. And so we start with the spots pattern, and we let the cellular automata to evolve for 30 steps. Then we compare it to the rings pattern, also obtained from the paper that I mentioned. We computed L1 loss, and then we let it evolve further for another 30 steps, and did it again on the rosettes pattern. And once we got these losses, we added them up, and we did backpropagation to adjust the parameters of the neurocellular automata to give us the desired output. And this is, unfortunately, it's a real pity. I can't show you what the transition is that the NCA learned, but you have to trust me, it's really beautiful. Like the transition is really smooth. And just to test out, we only had these 3 images, the spots pattern, the ring pattern, and then the rosettes pattern, and the NCA was able to model the transition very smoothly. Unfortunately, you can't see it. But this is not our end goal. We still want to get these equations to have like this understanding of the model. And to do that, I unfortunately don't have time to go in depth with you, but basically we had to adjust the architecture of the NCA. We actually coined the adjusted architecture as DINCA, Dynamic Identification Neural Server Automata, and basically we did that. We posed some kind of constraints on the weights. The constraint is here. It's only like an example of a constraint. We could pose another constraint as well, but for two variables we could pose this constraint. And what it tells us is that once we have the weights learned from the model, these are actually those weights that adhere to this law, and one can see that if we apply some clever weight pruning, we have what we wanted. We have the minimal PDE, and so this is what exactly the solution we got for this kind of process that the model was doing, and the equation for it. So a big thank to you for listening, and also a big thanks to the leopard. Without her, none of this would be possible.
Hello, my name is Jan, and I'll be talking about the paper. I'll be presenting the paper that has been accepted to the conference ACAI, and it's about machine learning for quantifier selection in CVC5. So, well, the thing that we are concerned about in this paper is automated theorem proving, and it aims to teach computers how to reason logically, right? This involves like proving statements, like using logical steps. You can think of it like a solving of a complex puzzle where each piece is a logical inference, and it is automated theorem proving in general is important for checking software, verifying hardware, and even for exploring new mathematical complex. And specifically we work with, in this paper, we work with SMT solvers, which are satisfied the modulo theory solvers, and which are specialized tools for automated reasoning. And they are designed to decide on satisfiability of a formula within a certain mathematical logic. They are used for wide range of applications, from software verification to verification of hardware. But the main challenge for SMT handling is handling of quantifiers, like existential and universal quantifier. And it is usually done by sort of alternation between the ground, something like SMT solver, and an instantiation model. So the ground solver sees the ground formula, and it also says some quantified formulas. It has some instantiation models, which suggest some instantiations for the quantified formulas, and then passes them back to the ground solver, and then in this way this continues. So, what are quantifiers? In logic, they allow us to express statements about collections of items. Like, for example, here we have for all x plus 1 is greater than x. SMT solvers handle quantifiers through instantiations, which means that they replace the quantified variable with some concrete values. For example, here we say that it should work for all numbers, so it should also work for some number 0, so we can plug in 0 for the place of x. And now, which quantifiers to instantiate and how? This is the main difficulty of the SMT solvers when they are trying to learn the deal with quantifiers. So what we do, we have the idea that we will use machine learning to intelligently select the sum of the quantifiers, and machine learning is trained to predict quantifiers instantiation which are good and which are positive and negative. This is the training samples are extracted from previous successful proofs. Each quantified formula is then represented by a numeric feature vector, and we train a gradient boosting decision tree to distinguish good and bad quantifiers. Then we implement this method inside the CVC5 SMT solver. CVC5 is a state-of-the-art SMT solver, one of the best currently, and it implements several instantiation models and each of the instantiation models uses different instantiation techniques, but all of them basically just inside they look something like this. They iterate over the quantifiers and then process the quantifiers one by one. So this is the place where we plug in the machine learning. We simply put one if here. So if the quantifier is predicted as positive by the machine learning, then we will process this, and otherwise we simply skip quantifiers which are considered by the machine learning model as useless. So now I can show you some of the results that we have achieved on a large collection of mathematical problems from Mizar Mathematical Library. So this is just a scatter plot of runtimes. So here we have basically what we want to see is that we want to see the dot behind the diagonal, because so we are comparing runtimes of two versions. So we have two runtimes, and we plot for each program, we plot a dot on that point. So the blue points under the diagonals are actually improvements, right? And then the red points are actually worsening. So this is what happens when you rerun the same solver again. So this is when you just start the same solver again without any machine learning, but with a different random scene. And this is what happens. So you see that you lose some problems, but you also get some problems. But it's sort of symmetrical. But with the machine learning, you see that we have much more blue bubbles here under the diagonal. So this is the improvement. So we can see that we have improved, like we have a lot of more problems solved, and there is also the cluster. Those are the problems that are not solved without machine learning, but here with machine learning we can solve them, and there are much less losses, right? And okay, so in the end, achievements, so we have used machine learning to filter quantifiers for instantiations in CVC5. We have nice results of machine learning with machine learning on Mizar Mathematical Library. We have improved the best strategy by 23%. The best known of portfolio of strategies is a collection of strategies. So we have improved the portfolio by 22%, and this is the state of the art of portfolio. So that's the best current results that you can get from CVC5, and we have improved it by 24%. And we even outperform other ATP methods which are even ML-enhanced and should work better with are specified for first topology. And there are some future road directions. So thank you. That's everything. That's all. Thank you.